All right, we're looking at Bezier curves in this video. Now, Bezier curves traditionally have been used for computer graphics. That's because they're sort of curvy curves and you can drag around these 4 points in orange. Now, this curve looks super complicated, but Desmos really likes to draw a whole bunch of extra lines that you don't need. The actual curve is this. So you can see the start and the end point do what they say. It's the start and the end point. And then these 2 points are the control points. So they sort of look like that. And they don't go through the control points, but they sort of control what sort of shape the curve has. I can't get it to make a happy face shape, and that's because you're about to see a horrible process of finding the equation. Let's have a look. So I've given you this here with those points, and we got to find the equation, and it's really awful. So the start point is x0 and y0. So x0 and y0 will be that start point there. Similarly, the finishing point is x3 and y3. And then the 2 control points we call 1 and 2. So x1, y1, x2, y2. We'd like to find the equations of this Bezier curve. So we start by finding this constant ax. This is x3 take 3x2 plus 3x1 take x0. All right, so let's start plugging in our numbers. X3 is 4. We're going to take 3 lots of x2, so that's 3 lots of 3. 3 lots of x1, so that's 3 lots of 2, and x0 was 1. So you probably can do these in your head pretty easily, but I like to make sure that I don't make a mistake, so I just type it in, so you get 0. It's not always 0, that's just a coincidence. Bx here, so that would be 3x2 take 6x1 plus 3x0. And just like we did before, we're going to get all of our numbers from these 4 points up here. So that's going to be 3 lots of, now x2 is 3, 6 lots of x1, so x1 was 2, and 3 lots of x0, so 3 lots of 1. And we'll see what we get there. So that's 3 lots of 3, take 6 lots of 2, plus 3 lots of 1. And you get 0 again. Again, this is just a coincidence, doesn't always happen like this. Cx is 3x1, take 3x0. This is going to be 3 lots of x1. So x1 is 2. And x0 is 1. Now you just get 3 for that one. And dx is x0, so that's just 1. Okay. Now what this tells us is that x of t is all that stuff. So axt cubed, so that's 0t cubed, 0t squared, 3t, and 1. So in other words, x of t is 3t plus 1. Okay, now time to do y. Halfway there. Ay, these are all the same equations, it's just with y's instead of x's. Now we're going to plug in what our y values actually are. So y3 was 0, 4, 3, and 1. So that will be minus 4 when we work that out. Now by is going to be 3y2 take 6y1 plus 3y0. So if we work that out, that's 3 lots of 4 take 6 lots of 3 plus 3 lots of 1. Okay. Now we better make sure we don't make a mistake. You get minus 3. All right, so next one. Cy is 3y1 take 3y0. So that would be 3 lots of 3 take 3 lots of 1. 6. And dy is y0. So y0 was 1. So that tells us that y would be this equation, minus 4t cubed. So that came from that number there, minus 4. Minus 3t squared plus 6t plus 1, just like that. So now we have our parametric equations for this Bezier curve. Wonderful. Now, just to verify that we have got this right, I'm going to sort of plot this all up on Desmos and see if it matches what we've got. So our starting point was supposed to be 1, 1, so I'll make that start around there. Our control points were supposed to be at 2, 3, so that's 2, 3. And our next one was supposed to be at 3, 4. Now, it actually does matter what order your control points are in, so just be careful about that. And then our endpoint was at 4, 0. This is just going to give us sort of an approximate of what we've got. So that's the Bezier curve. And I might put those a bit more on integer coordinates. There we go. If I graph my parametric equations, they should pretty much match. So that'll be 3t plus 1. And then my y parametric equation should be minus 4t cubed, take 3t squared, plus 6t plus 1. And you can see that red and the black line pretty much match. The only difference is that I haven't dragged the points perfectly, so they don't perfectly overlap. But they would if I placed the points perfectly. Note that Bezier curves always go from 0 to 1 on the t-values as well. Okay, next we need to find our leftmost points, rightmost points, and then our top and bottom points. So let's go the top and bottom points. Okay, so in any parametric curve, you're going to have like a whole bunch of stuff there. So at any of these points here, like that point would be y equals 0 because it's sort of flat in that direction. Sort of like a normal derivative. Similarly, you'll get this point here also equaling 0 on y. And I reckon because I've drawn that flat, I get 0 there. They're almost like points of inflection, but stationary points of inflection. So anywhere where it's flat, you get y of t is 0. You would have these 2 points here. So t equals 0 and t is 1. And then any points where it's flat in sort of the other direction would be x dash of t equals 0. Okay, so what you've got to do to find your leftmost and rightmost points, well, your top and your bottom points, is you want to solve y dash of t equaling 0 first. So y dash of t is the derivative of this stuff. So that's minus 12t squared takes 6t plus 6. And I reckon we should be able to solve that one. So let's pull out well, 0 equals that. Let's pull out a factor of minus 6. So you're left with 2t squared plus t, take 1. And we should be able to sum and product this, I reckon. So you've got 2t and t there. You would like two numbers at times to give you minus 1. So that would be minus 1 and 1. And let's see if we can trace these up and find it. So that's minus t, and that would be 2t times 1. And so if you add those together, you get positive t, and we got it. So one of our brackets is 2t take 1, and the other bracket is t plus 1. So what that tells us is that t is a half or t is minus 1, and we throw out that one because it's out of range. Okay, so t is half is the point that we're interested in. And then what we'd like to do is check. So basically this is step 1, is to find what I'm going to call the critical points. And then step 2 is to check both your critical points and endpoints. Okay, so what I might actually do is I might graph this Bezier curve in a calculator. So just as a reminder how to do that, you're going to go into graph and clear out whatever you've got in there. Set it to parametric mode, and we're going to go 3t plus 1. So the x button now does t for us in parametric mode. And minus 4t cubed, take 3t squared, plus 6t plus 1. You get those both graphed in there. We're going to go through this. We've got to set our window. So maybe I'll just go minus 5 to 5 just to get a really good view of what's happening. And t needs to go from 0 to 1 on a Bezier curve. Always 0 to 1. So we can see that there. So let's get our points that we want to check. So what we've got to do is we've got to check t equals 0, t equals a half, and t equals 1. Now the endpoints are t equals 0 and t equals 1, and our critical point is t equals a half, and we just got to check all three of those. So t equals 0, trace 0, enter, 1, 1. At t equals a half, trace a half, enter, 2.5, 2.75. You also can get this by subbing it back into the equations, like the parametric equations, because we just got t values. And t equals 1, trace 1, enter, 4, 0. Okay, so out of all these, I reckon our highest point is this one, so highest point there, and our lowest point would be the one where we've got 0. So the way that I'm checking that is I'm just looking at our y values, and I'm trying to see which one's the biggest and which one's the smallest. Okay, so that's the basically the process. Critical points, so y dash of t equals 0, and then you also check your endpoints. And from my diagram here, on this one, for example, your highest point would be that, and your lowest point would be that. And in that case, they're both critical points. But you can imagine that if this went like a little bit higher, that would be your highest point instead. So you do have to check the points on the end too. In this one, for example, our leftmost point is that, and our rightmost point would be that. So, for example, they're at the endpoint. So you do have to check both. So let's, in this question, check our leftmost and rightmost. So we're going to follow the same steps. So step 1 will be to find your critical points. And this is going to be for x dash of t equal to 0. X dash of t is 3. So we got no critical points. And if we sort of look at our Bezier curve, yes, there's a bit where it's flat top to bottom. That was at t equals a half. So it's sort of flat horizontally there. And you can actually see y to t is 0 there on the calculator as well. But there's no sort of lefty-righty flat bit. So we've got none of these green points on our graph. So all we need to do is we need to check the endpoints. So 2, we're going to be checking all of our points. So the only thing we have are endpoints. T is 0 and t is 1, and we actually found those endpoints before anyway. That was 1, 1 and 4, 0. And guess what? 1, 1 is your leftmost point, and 4, 0 is your rightmost point. And the way that I got that is just by looking at the x values for each of those points, smallest and biggest. And then hopefully we can see when we've got this graphed, the leftmost point there and the rightmost point there sort of makes sense. The top point was at the top there, and the bottom point was at the bottom, sort of at the end of our range.